Okay, we have looked at the implementation of a list using two different possible approaches. One is with a linked list, and one is with an array list. The array list itself is implemented using the more primitive structure of an array, but provides the additional benefit of not requiring the user to think about capacity. It manages the capacity for the user and allows the user to think at a higher level, not have to worry about some of those programming details. Well, there are other kinds of abstract data structures as well, like the list that we've talked about. For example, there's the stack and there's the queue. Now, if you recall, the stack and the queues were notable because of the way that they provided a different interface that enabled someone to put something on top of a stack, that was a push operation, or take something off the top of the stack, that was a pop operation. And a queue was like a line at a bank. And what that said, the way a queue worked is that when data shows up, it gets put in at one end, but it gets taken off the other end of the queue. These are abstract data types. They're operations that are defined, and those operations don't dictate the way that they're going to be implemented. Just like when you say you're going to implement a list, that doesn't dictate how it's going to be implemented. It can be implemented in several different ways, and we've seen two. So what we want to describe is we want to describe a choice. What would be a good way to implement a stack or a queue? As a systems programmer providing this to an API programmer? Well, there are a lot of different implementations that are possible. Move right. Well, if we think about a stack, we know a stack, everything is going to be put on and taken off one end. We just have to make sure that we keep track of that with a push and a pop. So an efficient way to do that would be to keep track of the stack as a sequence of nodes, thinking about it as something that's built on top of a linked list. When a new element is pushed onto the stack, that we can implement that by putting that element on one end of our sequence, our chain of linked list, our chain of nodes. And when you pop something off, we can take it off the same end. Well, what we want to do is we want to implement push and pop so that we can use the least expensive operation in order to make that operation happen. Well, push and pop are just, if we implement push and pop by using the linked list methods that we already have, add first and remove first, we can implement a stack that's very efficient in terms of adding something in constant time to the front of a linked list, push, and removing something in constant time from the front of our linked list, pop. Now imagine if we did that badly. If instead we decided to implement our stack as an array list, and we decided that we would push and pop things off the front of our array list instead of a linked list. Well, remember the implementation of an array list. When we put something at the beginning of an array list, we have to shift everything down. And when we remove something off the front end of an array list, we have to shift everything back. So a poor choice of how to implement a stack is the difference between a push and a pop taking 1 unit of time or a push and a pop taking n units of time. Let's say you have 1 billion elements in your stack. Would you like that to take 1 millisecond, or would you like that to take 1 billion milliseconds? It's a very weighty choice when the scale of your data structure starts to get large enough. So we think about that. If we are in the opportunity to implement a stack for a user, we choose the appropriate data structure to implement it so that the user has as much speed as possible and also gets the benefits of the abstract interface that we've provided, in this case, push and pop. Move right. Visually, this is just visually this is how we would do that. We would have a stack class that is almost exactly like the linked list class, keeping track of nodes, and when we push something on, we'd splice it into the chain at the front, and when we remove it, we would bypass the element at the front in the same way that add first and remove first was done in the linked list. We just call it something different. In fact, we could just keep a linked list within our stack class if we want to implement it that way. Move right. The actual code for this linked list stack implementation is available to you, and I'll put it on our website so that you can take a look at it. Alternatively, you could make a good decision about how to implement a stack with an array list. If you implemented your stack with an array list in such a way that instead of pushing and popping on the expensive side, the front end, if instead you did your push and your pop on the inexpensive end, the back end, then you could use an array list as a very effective and efficient way of keeping track of a stack. You just have to be careful that you put things on the correct end of the stack, the end that doesn't require all the shifting backwards and forwards. Now, it's true that occasionally when we add things to the end of an array list, we need to increase the capacity of our array. And so our array list implementation will periodically cost a little bit more. But on average, both the linked list implementation and a well-done array list, a well-done linked list operation and a well-done array list operation are both going to be about the same efficiency, order 1 or order 1 with a little footnote. This visually shows you how important it is to put the element at the correct location, either in an array list it's at the end. Move right. Similarly, we can make a decision about how to make a queue. And a queue puts things on one end of our list and takes things off the other end. We can implement a queue with a linked list very efficiently. We can add elements to the back of the queue, back of the linked list, and if it's a doubly linked list, this is an order 1 operation. And we can remove elements from the front of our list. And if it's a well-implemented doubly linked list, that's a constant time operation as well, as long as we keep a reference to our last element. So if we decide to implement a queue, add an element to the back, take an element off the front, just like a line at a bank, that is a very fast implementation. Both of those operations take order 1 time, a constant amount of time. Move right. You can see again visually that's a very similar operation to our stack, except that we're accessing and removing from both ends as well. Let's stop there for this lecture and give you some time to process and think about that. Thank you for your attention.